Hi everyone, I'm Chong. Welcome to my presentation on how to add fine-grained light control to diffusion models for image generation. This work was joint done with Youkang, Pieter, Youkang, Hongzhi, and Tong. Diffusion models are a very popular tool for prompt-driven image generation. Given text prompt describing the desired image content, a diffusion model outputs an image follows the given prompt. Besides the prompt, a diffusion model also takes a random seed as input that can be used to tweak the details of the generated image. Our goal is to add fine-grained light control to the diffusion model so that we can generate images that not only following the text prompt, but that also adhere to the provided lighting condition. Imagine an artist who wants to control the lighting of their generated images. They might want to choose from a variety of lighting conditions, ranging from environmental lighting to point lighting and to area lighting. Beyond fine-grained light control, we also desire to support these different lighting representations, although each of them can have different parameters. Another challenge is that the artist might also want to keep the content of their generated images fixed while having the ability to alter the lighting. This is difficult with current diffusion models. You can see that when changing the random seed in order to change lighting, we can see the texture of the original sphere shown on the left is also changed in the spheres on the right. For fine-grained lighting control, we desire separate control of image details and the lighting. The shading effects induced by the lighting can roughly be categorized as global and local. Global effects are due to large-scale geometry of the scene. This includes specular highlights caused by the curvature of the shapes and shadows due to parts of the scene, including others. Local shading effects are informed by geometrical details, such as bumps and scratches, rather than the global geometry. Our goal is to ensure that both local and global shading effects are correctly controlled. To overcome these challenges, we propose to first determine the image content in a separate generation stage. For every text prompt, we use an ordinary image generation model to generate the original image. This image defines the main content of our final image and can be fine-tuned while the content seed. We then convert various lighting representations into a set of pixel-aligned condition maps named radiance hints. We run depth estimation on the foreground of the provisional image to get a proxy geometry, and render the radiance hints under the target lighting with a homogeneous diffuse material and 3 specular materials under different roughness. We assume that the estimated geometry is accurate enough to model the global shading effects, but we do not expect that the estimated geometry includes all the geometrical details for correctly resolving the local shading details. However, combining these radiance hints with the provisional image is still very challenging due to the need of generating geometrical details and resolving the lighting material ambiguity in the single provisional image. Thus, we treat it as a generative problem and rely on another diffusion model to generate the final shading effects. To direct this diffusion model to follow the radiance hints, we encode the provisional image into a neuron texture, which is then multiplied with the radiance hints to get the shaded neural embedding, and sent into a specially trained control net to provide control of both the image content and the lighting condition. The control net combines global shading effects from the radiance hints, gives an interpretation of the material in the provisional image, and hallucinates local shading effects. By tweaking the appearance seed, we offer separate control of the local appearance details, including the interpretation of the materials in the provisional image. As a final step, we inpaint the background to form a full image. To summarize, our full 3-stage pipeline generates the provisional image from which we extract the proxy geometry in the form of a depth image, which are subsequently used to generate the radiance hints. These radiance hints are fed together with an appearance seed into a specially trained control net, yielding the foreground with correct lighting. Finally, consistent background is added. To train the control net for the second stage, we collect 25,000 objects with PBR textures. 13,000 of them are filtered from the observer's L width, and 12,000 are enhanced with other material maps. For each object, we randomly select 4 wheels, each under 12 lighting conditions, yielding a total of 1.2 million image pairs. Each image pair is supplemented with a target image and 4 radiance hints. To compensate for the limited diversity in the observer's dataset, we further enhanced the materials by assigning random homogeneous specular BRDFs with the original albedo maps, random homogeneous materials, and random SV BRDFs to selected shapes. Since the radiance hints are agnostic to a specific form of the lighting, we can easily include different types. During training, we cover a variety of lighting conditions from single and multiple point lights, area lighting, to environmental and monochrome environmental lighting. Now, let's look at some results. With the carefully designed pipeline and abundant training data, DiLightNet can generate high-quality images with fine-grained lighting control. Even though we did not enforce consistency between frames of the lighting animation, our results show good consistency, although not that perfectly, thanks to the fine-grained control mechanism. Our method works not only on objects with diffuse materials, but also on objects with reflective material properties under a variety of lighting conditions, including non-distant lightings like point lights. As mentioned before, altering the appearance seed directs DiLightNet to sample a different interpretation of light-material interaction in the provisional image. Due to inherent ambiguity of material definition in the single-input provisional image, DiLightNet also supports tuning the appearance details with text prompts. With a provided ground truth geometry, DiLightNet can leverage depth condition diffusion models to generate the provisional image and to produce more accurate global effects, such as the shadows on the table in this example. To summarize, we introduced DiLightNet, a novel method to add lighting control to diffusion-based image generation. Our method can provide fine-grained control under arbitrary lighting conditions. We hope DiLightNet will benefit methods for real-world material estimation and image to 3D generation. As with all diffusion models, more training data is better, and we expect that DiLightNet will benefit from the availability of future large-scale real-world object PBR datasets. Thank you for your attention. Please visit our project page for more results and details.